All right, in this video, I'm going to be working some more weak acid problems for you. So here is the first one. The pH of a 0.37 molar solution of hydrofluoric acid, HF, is 1.82. What is HF's pKa? So I've talked about this before, but I think that these kinds of questions are really innocuous looking. Like you're looking at it and you're like, well, this should be a piece of cake. But it's not. These questions require a lot of work to be done. You can't just like look at it and bam bam like figure out what the answer is. So let's take it apart piece by piece so that you can understand what's happening. So the pH of a 0.37 molar solution, so that's our initial concentration. It's a solution, so we know that water is also in there. You can't have a solution without having some kind of solvent. The solvent in this case is water. I know I don't say it's aqueous, but acids are typically in aqueous solutions. And we know that the pH of that is 1.82. We'll come back to that in a second. But let's focus on what it's asking us for. So the question is asking for what is HF's pKa? So let's remember what a pKa is. The pKa is basically how tightly the acid wants to hold on to its proton. A low pKa means the acid doesn't want to hold on to its proton, it wants to let it go. So the lower the pKa, the stronger the acid. So what else is pKa? pKa is the negative log of the Ka. Just like pH is the negative log of the hydronium ion, pKa is the negative log of the Ka. So we're going to look at this in, kind of that relationship. And so basically what this question is asking for is what is the Ka? I mean, we can put it into this equation and figure out what the pKa is looking at the negative log, but basically we're looking for the Ka. So what is the Ka? Ka is the equilibrium expression constant. The acid ionization constant, because this isn't Ka, and we're talking about an acid. So we want to know what is the value of that Ka. That's what this question is asking for. So let's write it out. We know that this is going to be an equilibrium because HF is a weak acid. We know that we're trying to solve for the Ka. That's products to its orders divided by reactants to its orders. So let's actually write out this equilibrium, see what we have, see what we need in order to figure out what this Ka is and therefore what the pKa is. So we're going to put HF, hydrofluoric acid, into water. HF is a weak acid. Weak acids are at equilibrium. Arrhenius tells us that we're going to form hydronium ion and then the counter ion of fluoride. So we know that the Ka is going to be equal to the concentration of hydronium to the first times the concentration of fluoride to the first divided by the concentration of HF to the first. Again, watch those coefficients. It just so happens that all these coefficients are 1 to 1 to 1, so we don't have any orders in here. But that is not always the case. So please be careful and watch your coefficients. All right. So we need to solve for the value of the Ka, which means that we need to solve for this side of the equation. That means that everything on this side of the equation has to be something that we can get. This is a clue to you that there's going to be no assumptions. You only make assumptions when you're solving for x. In this case, we are not solving for x, we're solving for Ka. Since we're solving for Ka, there will be no assumptions. So let's complete this ICE table so that we can figure out what's going on. The initial concentration of HF is 0.37. We do not care about water. And I realized before that I probably should go like this because it kind of looks like an X. But we don't care about water. Water is 55 molar. It doesn't change. Water is taken into the Ka expression. We don't have to worry about water. Initial concentration of hydronium ion is 0. Initial concentration of fluoride is 0. The equilibrium will shift to the right to make up for the fact that we have no products. So the change is that we're going to lose 1x because the coefficient in front of the HF is 1, the coefficient in front of the X is 1. Again, watch the coefficients. It just so happens that it's 1 to 1 to 1 here. It will not always be. So please be careful. Do not fall into the trap that the coefficients are always 1. I'm going to erase that because that's ugly. Okay, we don't care about water. We're going to increase the concentration of hydronium ion by 1 because its coefficient is 1. We're going to increase the concentration of fluoride by 1x because its coefficient is also 1. At equilibrium, the concentration of HF is 0.37 minus X. The concentration of hydronium is X. The concentration of fluoride is X. Again, no assumption. We are trying to figure out what the value of Ka is. And so therefore we would have, we don't know what Ka is. And if we didn't also know what X was, we would have two unknowns. We only have the one equation, so we have to have some other way of getting at what each one of those unknowns is. So the Ka is what we're solving for. We must have some information in the problem letting us know what X is. And I wrote the problem, so I know that to be true. The pH is 1.82. pH is the negative log of the hydronium ion concentration. 10 to the minus pH is hydronium ion concentration. So 10 to the minus 1.82 equals the concentration of hydronium ion. So the concentration of hydronium ion is equal to 10 to the minus 1.82, 0.015. Let me double check my math. 10 to the minus 1.82, 0.0151. So what does that mean for us? That means that X equals 0.0151. We know the concentration of hydronium. Fluoride concentration at equilibrium is also X, so that's 0.0151. The equilibrium concentration of the HF is 0.37 minus 0.0151, giving us the concentration at equilibrium of 0.355. Now we can solve for the Ka, and in solving for the Ka, we can solve for the pKa. The Ka is equal to hydronium to the first. Hydronium to the first is 0.0151 times fluoride to the first. Fluoride concentration at equilibrium is 0.0151 divided by HF to the first, 0.355. That equals 0.0151 times 0.0151 divided by 0.355. I'm going to multiply that by 100 to get it in scientific notation. 6.42 times 10 to the minus 4th. That's what the Ka is equal to for HF, for HF in general. And then we're going to figure out what the pKa is. The pKa is the negative log of the Ka. Negative log of 6.42 times 10 to the minus 4th. The pKa is negative log 6.42 times 10 to the minus 4th, 3.19. So again, what I really want to emphasize is this question looks so innocuous. It looks so straightforward and like you'd be able to just like figure it out, but there's a lot of work that goes into these. What is the pKa? What is the pH? There's a lot of work that goes into it. Okay, one more. Benzoic acid has a pKa of 4.19. What is the pH of a 0.15 molar solution? So again, let's delve into this and figure out each piece to help you out along the way when you're on your own with these. Benzoic acid has a pKa of 4.19. Now, right off the bat, I've usually had students who have started to panic about this. They're like, I don't know what benzoic acid looks like. No, of course you don't know what benzoic acid looks like. I know what benzoic acid looks like, but you don't. But does it really matter what the structure of benzoic acid is? And I'll tell you, it doesn't. All that you really need to know for an acid is that acids give away their protons. So benzoic acid here has a proton affinity of 4.19. It wants to give its proton away pretty good. It's a little bit of a weaker acid than HF. HF's pKa was 3.19. HF only wanted to hold on to its proton 3. Benzoic acid wants to get rid of it a little bit more, less readily. It wants to hold on to it a little bit more than HF. So it's going to be a little bit of a weaker acid than HF. But it doesn't really matter what benzoic acid looks like. You can write a generic acid as HA. What that really stands for, what you can think about it standing for, is there's a proton. H is a proton, and it's just bonded to or, associated with an anion. So HA can be just any generic acid, monoprotic, it has one proton to give away, and then you have that generic anion off of it. So we're going to just show benzoic acid as being HA. Now, please, don't make every acid generic. That will make me very cranky. I do expect you to know what acetic acid looks like. You cannot just give me HA for acetic acid. But for other ones that we haven't discussed, like benzoic, absolutely. You can generify it, not a word. You can make it generic by calling it HA. Okay, what else do we know about this? We know that it has a pKa of 4.19. That means that we also know that its Ka is 10 to the minus 4.19, which I likely have written down somewhere. 6.46 times 10 to the minus fifth. Okay, so we know it's a weak acid, kind of on the same order of acetic acid. What is the pH? pH is the negative log of the hydronium ion concentration. So basically this question is asking, okay, what's the concentration of hydronium? We'll find the concentration for hydronium and then take the negative log of it to get the pH. And we know that it's a dilute solution, 0.15 molar. It's a solution, so water is also around. So it's a weak acid. It is an equilibrium. Let's write the equilibrium. HA is our generic benzoic acid, reacts with water that is in equilibrium with hydronium ion and A minus. Just like HF gives you H plus, hydronium ion and F minus. Acetic acid gives you hydronium and acetate ion. HA gives you hydronium ion and A minus. The initial concentration of HA, benzoic acid, is 0.15 molar. We don't care about water. The initial concentration of hydronium is 0. The initial concentration of the anion of benzoic acid, also called benzoate, is 0 as well. The equilibrium will shift to the right. The reason it will shift to the right is because we have no products, and we need to have some products at equilibrium. HA will decrease by 1x because its coefficient is 1. Hydronium will increase by 1x because its coefficient is 1. A minus will increase by 1x because its coefficient is 1. At equilibrium, we have 0.15 minus x, x, and x. Excuse me. So now, we're going to make an assumption. We know what Ka is. We know that it's 6.46 times 10 to the minus fifth is equal to the concentration of hydronium to the first times the concentration of benzoate, A minus to the first, divided by the concentration of HA to the first power. We know the left-hand side of that equation. That means our variable, what we're solving for, is going to be in the right-hand side of the equation. That's where x goes. So to make our lives easy, to simplify the math, we're going to assume that at equilibrium, that's going to stay about 0.15. So now we can plug that into our equilibrium expression, our acid ionization constant expression. 6.46 times 10 to the minus fifth equals x times x divided by 0.15. 6.46 times 0.15, Square root of that gives you 0.00311. Check the assumption. We made the assumption that the change is negligible, and so we have to check to make sure that it is valid. You can't just keep going on. This is another step students like to miss, students like to skip, especially if they're going too fast. Make sure you check the assumption. So we're going to put x divided by the initial concentration of 0.15 times 100. It turns out that it's 2%, so check, we're good. As long as we're less than 5%, we can carry on using that assumption. If it's greater than 5%, then you're going to have to use the quadratic equation or more complicated math. So our assumption is valid. So we know what x is. X is the concentration of hydronium. So we were asked, what is the pH of this solution? pH is the negative log of the hydronium ion concentration. Now we know what the hydronium ion concentration is. So the pH is the negative log of the hydronium ion concentration, which is 0.00311. So this pH is equal to 2.51. Again, it's a weak acid, but it still has a low pH. Okay, so weak acid does not mean neutral. It does not mean basic. Weak acid means acid, just not super as acidic as hydrochloric or something like that. So 0.15 molar still has a pH of 2.5, which is pretty acidic. All right, in my next video, I will talk about why is neutral pH 7.